So I'd like to introduce our next speaker, which is Gretchen Benedix, and Gretchen's from Curtin University, and she's going to talk to us a lot about water. So I'm going to hand over to you, Gretchen, and we're along for the ride.
Okay, let's see how we go. All right, so I'm going to fight the microphone with my glasses because I forgot that I have glasses on. Okay, so I am from Curtin University, and I am normally a mineralogist, petrologist. I had the chance to work on Murchison when I got my second post-doctoral job, where I started off doing just mineralogy and petrology, so looking at different minerals and different asteroid meteorite types. And then I went and I learned a lot about how to understand water in meteorites. And that was when I was introduced to looking at Murchison. So that's kind of where I'm coming from. But my current day job is actually trying to understand the surface geology of Mars. So it's been a little while since I looked specifically for evidence of water. I can see it all over Mars in terms of what the surface of Mars looks like, but I can't find the actual water there. So we'll do a little bit of chatting about how we get to understand about water in space. But before we do that, we kind of have to think about what is water. So what's the definition of water? So I looked this up on Google earlier today because, it feels like, the definition of water should be really straightforward. And part of it is that it is the basis of the fluids of living organisms. So that's a good thing for us to know. The other thing is that it says that it's a colorless, transparent, odorless liquid that forms the seas. We see those around a lot. Forms lakes, which I don't have a picture of here, rivers, that's the Amazon River, and rain. And this is how we see water on Earth. Water on Earth occurs in a lot of different places. We see it, it rains on us, we swim in it and whatnot. But water is not just a liquid. Water, as the term, it's composed of hydrogen and oxygen, H2O, we know this. But H2O can exist in other forms. So on Earth, we have H2O, and it exists as ice. So this is Antarctica, big ice sheet, but we find ice in different places on Earth. But we also know that water can exist as a gas. So there's water in our atmosphere. There's water that is coming out of volcanic regions. So this is Yellowstone National Park in the United States, which has these big hydrothermal vents that exude steam, water steam. So when we say water, we kind of have to be a little bit careful. So for most people, water just means here's this stuff I'm going to drink or swim in or get wet by. But when you talk to some scientists, you have to kind of talk about, well, what kind of water is it? Is it a solid form? Is it a gas form? So let's have a think now. If we're in space, what kind of forms do we have? All right, so here are a few bodies from space that range in size. So I couldn't find any images of what we might consider water to be on Mercury or Venus. They're just some strange planets that we have. But we have some evidence for Mars in that we have some old craters, impact craters, that are filled with ice that we can see from space. If we travel out a bit farther into the solar system, we come to Jupiter, and Jupiter has a bunch of moons, some of which are a bit icy. So this is Europa, and Europa has a big icy cover on its surface. Its crust is all ice, water ice, and underneath might be liquid, but we're not sure. We think so. This is Ceres, which is a dwarf planet, and it used to be the biggest asteroid, but there was a big to-do in 2006 where Pluto got demoted from being a planet, so they had to promote Ceres from being an asteroid, so it's now a dwarf planet. So it's actually the biggest small body we have out there in terms of what we used to call asteroids. And you can see that it's got some bright spots on here. Ceres is also of a composition that we kind of think might match carbonaceous chondrites. So this could possibly be something like where Murchison formed originally. This is probably not the body that Murchison flew away from, but it could be similar. So this is sort of what we've got for space. So let's think about this. Why would we have these different forms of water? So I'm going to give you a bit of a chemistry lesson, but I'm going to go really slowly. And we're going to talk about something called a phase diagram. So I teach this to mineralogy students. And what we're going to talk about is why do we see water happening in different forms in different places? And what we're going to talk about specifically is we're going to talk about how things change, whether it's based on temperature or on pressure, because temperature and pressure can change what we're looking at. And we have to think about how these things are different outside of Earth. Earth is a really interesting place in our solar system, but it's a little bit unique. So if we want to put our Earth into context, we kind of have to figure out where do we fit, and then how do we fit these other things into it. So we have this pressure and temperature, and what I've drawn on here very poorly are some lines, and those lines indicate areas where the water, the H2O, will exist as a gas, where it will exist as a liquid, and where it will exist as a solid. And these are ranges of temperatures and pressures, so we can figure out that sort of thing. So let's start with Earth, all right? So at sea level, the Earth's atmospheric pressure, so the Earth has an atmosphere of gas, it has a specific pressure that allows us to see things. So if we start on Earth, this is sea level, and that is where the average pressure is about 1,000 millibars. I've done things in millibars, but there are about 100 million different units for pressure because everybody measured it in different ways. So I've picked millibars, but if you were talking to somebody from back in the day, it would be millimeters of mercury. Or if you were talking to someone who looks at impact craters, it would be gigapascals. So anyway, we're talking millibars. So 1,000 millibars at sea level, your water will boil at 100 degrees. And your water will freeze at 0 degrees. Okay, so that's all making sense. That's pretty good. Anybody ever been to the top of a mountain? A relatively high mountain? What happens to your water there? Does it boil at 100 degrees anymore? No, it doesn't. And this is why. So if we have a different pressure, so if we go to the top of Mount Everest, which is quite high, the effective atmospheric pressure there is a lot lower. So your water will boil at a much lower temperature, probably about 70 degrees, maybe a little lower than that. So this is giving us kind of so here's kind of our range on Earth. This is what we look like here on Earth. Now, I showed you before Antarctica. So if we're looking at Antarctica, and we were to plot in, Antarctica is actually relatively high in terms of its elevation, and its annual mean temperature, because it's on the bottom of the southern hemisphere, it actually doesn't get that much sunlight. So it's actually pretty cold. So if we were to plot Antarctica on this diagram, this is about the range of temperatures and pressures that you would expect in Antarctica. So that explains a lot about why we're only ever seeing ice there. It's just got that solid formation there. Okay, so now, let's say we want to go and see what's going on out in space. So this is the average pressure, atmospheric pressure at Mars. So Mars is about half the size of the Earth. And what we see, this is the current atmospheric pressure. That's what we measure when we're there. And what we can see is that over the whole range of temperatures that we have on Mars, the hottest it's ever been recorded is probably somewhere here. So what we're seeing is that you're not going to see much liquid water on the surface of Mars, if any. We might find some evidence for it, but we really can't. The average temperature for Mars is way down here. So it's sort of Antarctic temperatures. Okay, so that's interesting. So now we go to Europa. Let's have a look at Europa. So Europa's average atmospheric pressure is really, really low. Europa's really tiny moon. So this explains why we can only see ice on its surface. When we go below the surface, we can increase pressure, so that's why there may be liquid water on Europa, but we have to get below that surface and find that pressure. Now, these all have some slight, tiny amount of atmosphere, kind of gas, to hold that in. On an asteroid, there's no atmosphere whatsoever. So trying to figure out water, would water even exist? Could we get it in a liquid form at any point? The pressure differences inside of an asteroid are actually pretty small as well. So this is what kind of leads us to Murchison, and I'm going to steal this beautiful image, which is from the Smithsonian, but Trevor kindly showed us before. So Murchison, we look at Murchison, and at our first glance, we see a black rock. So what are we looking for? What could we see in here? How is this going to teach us about water from space? So what we do is we start to think about it, and as a mineralogist, petrologist, I want to look at the sample in thin section. So I like to take a thin slice, and I want to cut it, and I want to look through it. Now, with a lot of rocks, volcanic rocks, for instance, the minerals are really clear. You can see right through them. So you shine a light through them, you can see through them. It's fantastic. You're like, oh. You put a polarizer into your microscope, and it's colorful, and it's gorgeous, and it's beautiful. Now, with Murchison, what we can do is we can see some of that if we're looking at those white bits where there's chondrules, the spherical things, or the CAIs. But for the rest of that dark matrix material, that dark stuff, you cannot see through that with a microscope at all. So what we've done is we've sort of taken two ways to look at it. So this is an image of a thin section, but this isn't an image taken by an optical microscope. This isn't with light. This is with electrons. So we can fire a beam of electrons. It's kind of like a light bulb. Fire a beam of electrons at the surface of a rock, and it will reflect back some electrons. It will reflect back some X-rays, and we can do a lot with that. So we can see areas that are brighter and areas that are darker. On this particular map, that tells us where some elements are heavier, so there might be more iron here. And here might be where there's elements that are lighter, so that might be more magnesium rich. But what this gives us is kind of a feel for what this looks like across the whole sample. So this is what I did when I was trying to figure out how do I want to understand water in Murchison, or how do I want to understand water from space. Now, I should give you a scale because I'm a geologist, and that's clearly what we should always do as geologists. So this is roughly 2 centimeters across. So it's not huge. It fits on a slide that's about 2.5 centimeters across. Now I said this is electrons. So this is reflecting electrons. But what I'm going to show you next is what we get when we analyze the X-rays. Because the X-rays tell us about what actual elements are there. All right, so this is an image of the elements. And what I've done with this, it's kind of pixely, is I've actually mapped this section. And I've taken the map that I did for calcium, the map I did for silicon, and the map I did for magnesium, and I mixed them together. And Photoshop is a wonderful thing. Photoshop lets me mix them together, and then I can use my color wheel from when I was in kindy or pre-primary, and I can say, okay, if I have red and blue, I'm going to have a purple color, and if I have green, it's kind of weird, but in Photoshop, if I mix green and red, I get yellow. And then I can have some tealy bits with the silicon and the magnesium mixing, the green and blue. But this lets me kind of look at this now and say, there's things here I can learn about to figure out what's going on. So what I've got is I've got a lot of bright blue stuff, and that's the stuff that's dry. And then I have some red things in here. Those are really, really calcium rich. We're going to come back to those. And there's some yellowy bits in here. So this allows me to map out mineralogy. I know there's olivine in here. I know there's pyroxene in here. I know that there is some various and other bits and bobs. I'm going to give you the clue right away that the red stuff is carbonate. It's calcium carbonate. That's why it's just red. It doesn't mix with silicon. So when we analyze Murchison specifically, if we were to look at this down a microscope, we would see something. And if we were to look at this, we would see something that looks different. But with an optical microscope, it's a little bit hard. But what we're looking for here and what we're finding, and this is how we get back to the water that we found in Murchison. If we take a bit of dry rock, so this is a chondrule from a carbonaceous chondrite, you can see these minerals, they're very clear. They're quite pretty. If I put a polarizer in there, we'd get beautiful colors. It would look like a stained glass window. If we add water to that, we have a reaction. That reaction makes a new type of mineral. And this is what the new thing will look like. So it won't be the nice big grains that we see there, the big crystals, we'll see a bunch of tiny feathery things, and it'll all be kind of a bit cloudy and a bit mushy. These are clay minerals. So these are clay minerals that you'll find out, just next door. You're on an unconformity here, I understand. So there's clay minerals around. So this is one way we know that water interacted with Murchison's rocks, is that we see the evidence in some of them. And we see that it's in between. So we can see areas that didn't have water, and then we see areas that did have water. And we can analyze those. We can determine how much water do you need to make something like this. And we can look at the whole section, the whole rock that we look at, and try to figure out, okay, if this was all dry material to begin with, how much water would you need to make this much clay mineralogy? But clays aren't the only things that we find in the Murchison meteorite. So the other one we find is carbonate, calcium carbonate, lime scale. So this is actually, I'm going to point out some interesting things here. I found this, it's very cool. But what we're doing is, lime scale is just a combination of calcium and what we call the carbonate molecule. So it's calcium, carbon, and oxygen all mixed together. But to get to calcium, carbon, and oxygen, there's a reaction that occurs. So I'm blowing this up. Now, the reaction that is actually happening to form this thing here is between water and CO2. So that means that on our rock, we had to have some water, and in this case it says it has to be liquid form, and that could react with dissolved CO2. Now we know there's carbon on Murchison because we know there's amino acids there. So in the forms of these, or during the processing that occurs on Murchison's parent body, it's possible that you're taking that carbon from the amino acids and you're converting it into this CO2, this carbon dioxide, which then reacts with whatever form of water is in there. We think it probably could be liquidy, but we're not sure. And that's going to help us form the the carbonate that we see. But these two together form that, which reacts with the calcium ions, which Trevor was just talking about in the calcium aluminium-rich inclusions. I've learned over the years. I can speak both languages, English and American. That allows us to see that we have some amount of water in there. And part of what I did in my postdoctoral work was to actually analyze the oxygen isotopic composition of the water, because the carbonate is one of the few that doesn't have a whole lot of its oxygen, that gets most of its oxygen from its water, rather than in a mineral we have oxygen combined to some of the other metals. In the case of carbonate, that oxygen is primarily coming from the water in the system. So let's go back to our, I'm going to do this very quickly, and we're going to zoom in. It's not the best resolution, but I'm going to zoom into this area. So if we're looking at this is again the electron map. Grayscale, we see some dark and some light. It doesn't really help us figure out where things are. But if we look at it this way, it's very pixely, but all the red things are carbonates. So we can go in and analyze each and every one of those carbonates in a bunch of different ways. What we learned from Murchison is that most of the carbonate was formed by this water CO2 reaction plus the calcium from someplace, whereas in some other CM2 chondrites, the carbonates have actually, the water had a lot more other elements in it, like magnesium, so it went to another form of carbonate that was formed. But the green, all of the kind of greeny colors in here, instead of the teals, yellows, and blues, that's all the clay mineralogy. So you're seeing this wide range of clay mineralogy from that. So I'm getting us back on track here. So what has Murchison told us? So based on some of the work I did, but a lot of what has been done over the years is we know that water interacted with these dry minerals to form clay minerals. So we know that was a form of water, most likely some kind of liquidy, but perhaps not liquidy. We also know the carbonates means water had to be there. But we have a lot left to learn. What else do we need to know? Well, what form was that water? So it could be liquid, but it'd be really hard given all that pressure and temperature that I talked about earlier. How do we get liquid? But tomorrow you can see a talk by Professor Bland who will explain mud as a form of water. How much water? We can actually try to work out how much water might have been there. We need more samples. Murchison is a fantastic sample. It's huge. We can look at a lot of it. But the more samples we have of the same type, that allows us to actually work out how much water might have been present. We can also get to how did we get water on Earth? Is all the water that we have on Earth coming from the Earth itself during its accretion? Was it accreting Murchison-like bodies together and then all of that water kind of extruded because we had enough pressure to hold on to it? Or did it come on comets? Or is it a combination of things coming out from accretion of the Earth's materials and cometary input and asteroid input because Murchison has water in it somehow? And finally, because of the amino acids and the water that we're finding in Murchison and some other CMs, does that tell us things about life? Does that tell us that life actually formed out in space and then came to Earth on these bodies? Did it form here and spontaneously come out because we actually had a lot of water here already? So there's a whole bunch of things that we would like to continue to learn about this, and Murchison is helping us continue to do that. Thank you very much. Did I really go that long? I'm sorry.
Thank you, Gretchen. Gretchen, a small token from the
Thank you.
community of our magnificent world.
Lovely. Very nice.
Thank you for a magnificent talk.
No worries.
Before you disappear, are there any questions about water? Yes.
Well, it's not really about water. What I want to know is, do you ever find things that you don't know about?
At the moment, no, but we haven't gone all the way down to the smallest things that we can access yet. But we do find new minerals sometimes. So, like in Murchison, the Murchisite is a new mineral form. But mostly, the elements that are there, it's only going to be how those elements go together and whether we've seen that sort of formation before. But then that tells us things about temperatures and pressures of how they form.
Andy?
Thanks for that. One of the big questions, of course, is where did the Earth get all this water? Is this a suitable source?
Well, this is one of the options now, that it's not all coming in on comets. It's perhaps a combination of the original accretion of the bodies that formed the Earth, then volcanic outgassing causing that water to form, and then it being supplemented by asteroids that are hydrated. So asteroids coming in that have water in them that contributes to the whole thing. It could be both, yeah. Because I think there has been work done in the past that you can analyze, like the oxygen isotopes that Trevor was talking about. You can analyze the oxygen isotopes. You can determine the isotopic composition of comets, and those two things, or maybe it's the hydrogen isotopes, those two things don't completely match. So it looks like it's a combination of things.
Gretchen, that's a lot of clay.
Yeah.
Volumetrically, what is the implication for the amount of water in clays in the early solar system? Do we have a feel for this?
There's a calculation there. I vaguely recall that this was sort of like 60% water, I think.
It's a lot of water.
It's I can't quite remember the ratio, but it was slightly more water than rock. So it might be 50-55% water.
So if we deliver a lot of these meteorites to Earth and heat them up, they're going to release their water.
It feels like, yes.
That's right.
Yeah, sure.
Pretty cool way to do it. Please thank our first three speakers.